Hey everybody, I'm Mr. Cozad back again for another video lesson. Our concept for today comes from our textbook, our Algebra 2 textbook 4.4, and we're going to talk about complex numbers, okay, aka imaginary numbers. This is a really fun concept because up until this point in your math career, you've been told they're only operated with real numbers, but today we're going to operate in this realm of complex numbers or imaginary numbers. You'll learn today what they are, and you'll learn how to add them, subtract them, multiply them, and solve problems with imaginary solutions, okay? So if you are my student in class, you should either have a copy of these notes already, or you can pause right now and go to It's Learning and download the blank copy of this notes, print it, and take notes as you go. If you've stumbled upon this video just by searching the YouTube, you, first of all, welcome. You can just take notes on a blank sheet of paper or just kind of watch and listen as you go. Okay, so there's quite a bit to get through today, but it goes pretty fast. So let's jump right in. So, of course, we need some comics. Teacher says, "Why are you turning in a blank sheet of paper?" Because all my answers are imaginary numbers. That's a good joke. I have a couple of you students in mind that would actually try this. Please don't do that because you will not get an imaginary 0 on your grade when that happens, but kind of funny. All right, so here we go, the good stuff. What are imaginary numbers? So we know and can simplify positive roots. You've taken the square root of positive numbers countless number of times over the last few years. But what about negative roots? What about negative roots? Okay. Well, for example, think about the square root of -4. If you think about that, we could rewrite the square root of -4 as 1 times 4. Okay. Think about that. All I've done is I've changed the complexion of -4. I've divided out a -1 or factored out a -1, and I have -1 times 4. Well, properties of radicals tell me that I can split this up into 2 different square roots. I can take the square root of -1 times the square root of 4. Well, the square root of 4 should be familiar to us. Okay, we know that that equals 2. So really what this boils down to is when we take the square root of negative numbers, really the only thing that we don't know is the square root of -1. If we could figure out what the square root of -1 equals, then we could solve negative square roots. Well, mathematicians kept coming to this conclusion. They kept realizing that, really the only thing we don't know is the square root of -1. So what they decided to do is call that the imaginary unit. So anytime that they encountered these old mathematicians and us today, anytime we encounter the square root of -1, we can replace that with a lowercase I. And again, this is called the imaginary unit. It's called the imaginary unit. So if we go back to that problem that we originally looked at, the square root of -4 equals 2i. And we contrast that with the square root of +4 is just 2. The square root of -4 is 2i, where again, I is the imaginary unit. Now, there may be 1 or 2 of you that are asking yourselves the question, well, don't you need a plus or minus in front of those numbers when you evaluate the square root? And technically, yes, there are 2 numbers. There's both the positive and the negative that give you those values. But typically, what we do is we just look at the positive root, which is called the principal root. Your textbook goes into that a little bit more detail, but this is called the principal root. Okay, let's write that down. It's called the principal root. The principal root, again, is only positive. It's only positive. Okay? All right, so, of course, more comics. Shrink, counselor, do I really exist? That's a good joke, too. Oh, man, I hope you laughed out loud. Don't make me feel weird about being the only one laughing at that. That's a good one. And one more. 2 says to 3, hey, you guys want to meet my new friend? Sure, but where is he? He's right here. Why can't anyone else see you? Beats me. Get it? Because he's imaginary. Oh, that's a good joke. Okay. All right. Enough of the fun stuff. Now let's do the really fun stuff. Okay. So here we go. So these are some problems that you're going to have to simplify. Some of them are really, really simple. Others of them are a little bit more complicated. Okay. But let's start with example 1. Okay. Example 1 is the square root of negative 64. Okay. Well, the first thing that we recognize is we really can separate this into two numbers. We can separate it to the square root of negative 1 times 64. So when I do that, very clearly what I see is I've got the square root of negative 1 times the square root of 64, two separate square roots. Well, when I evaluate that, I know from the previous few slides that anytime I encounter the square root of negative 1, okay, I replace that with the imaginary unit, I. So the square root of 64 is a root that we should know. It's 8, and then we put the I at the end, 8i. And again, we're just looking at the positive root here, so that's called the principal root. It could also be negative 8i. There are two possible outcomes here, but again, when we're simplifying expressions like this, usually you just are looking for the principal root, which is the positive root, okay? If we look at example 2, eventually you're going to get really fast at this and you're not going to have to show much work. You're going to know that we can split this up into the square root of negative 1 times 9. You're going to know that the square root of 9 is 3. And again, there's that imaginary unit again, 3i. Okay? Now sometimes you'll be asked to simplify negative square roots that are not perfect squares, okay, like the example of negative 108. So negative 108, we can again split it up to negative 1 times positive 108, and then think about what we can do with 108. 108 is 36 times 3. Okay, it's 36 times 3. So if we evaluate this, the square root of 36 is 6. The square root of negative 1 comes out as an I, and this poor little square root of 3 is trapped in there forever. So this simplified expression is actually 6i root 3. 6i root 3. Notice that one of the common mistakes that when you take the square root of negative 1, you do not need a negative sign attached with the I. Remember, anytime you see I, that's just a substitution for the square root of negative 1. It's the imaginary unit. Okay. Now, on example 4, okay, we're going to combine what we know about radicals from the past. Okay, and we're going to actually, no, I'm not going to do it like that. I'm just going to rewrite it. We're going to split example 4 up into the square root of negative 8 all over the square root of 3. Okay? Now, hopefully you remember that we're not allowed to leave radicals in our denominator, so I'm going to go ahead and just get rid of that so I don't have to worry about it anymore by multiplying by the square root of 3 over the square root of 3. So the top becomes the square root of negative 24 all over 3. Now, you're not going to stop here. You're going to see what you can simplify with the square root of negative 24. Okay? Well, negative 24, we can do negative 1 times, so for 24, we could do 4 times 6. 4 times 6 would work. The reason that I picked 4 times 6 is because 4 is a perfect square. So that's going to come out as a 2. The negative 1 comes out as an I. But that poor little 6, root 6, is stuck in the radical forever. It can't come out. All over 3. Now this is actually your final answer, okay? Don't be one of the people that sees, oh, but Cozad, wait a minute, there's a 3 and a 6. I could divide the 6 by 3. Well, no, you can't, because this 6 on the top is still inside the radical. The 3 on the bottom is not inside the radical anymore, okay? So you can't simplify or factor if the top's in the radical and the bottom is not in a radical. So this is our final answer. Okay, hopefully those were pretty easy for you. It's basically the same, similar concept to what we've learned in the past. The only change here is that you are introducing the imaginary unit. Okay. Of course, one more comment. This is probably my favorite one. Mom, Some kids at school today called me 4i. Get it? Because it's the square root of negative 16, which equals 4i. That's a good comic. Okay, all right. All right, here we go. So here's the next concept of complex numbers or imaginary numbers that you're going to be expected to know. Some of you are hopefully still laughing about this comic, 4i. That's a really, really good joke, by the way. I hope you gave it the appreciation it deserved. Okay, back to the math. So powers of I are kind of interesting, okay? There's actually going to be a repeating pattern that you're going to see when you increase the power of I. Okay, so Koza, what do you mean? Okay, well, I to the first power is just I. Okay, anything to the first power just stays the same. Okay, well, I squared, okay, if we think about what I squared is, we can substitute square root of negative 1 in for I. So what this really becomes is the square root of negative 1 squared. Well, when you take a square root and you square it, those cancel out. So I squared actually equals negative 1. So now think about I to the third power, okay? So I to the third power is we take negative 1, I won't do that just yet. I to the third power, we can think of it as I squared times I. Because if you take I squared times I, that will equal I to the third power. Well, we've already shown that I squared is negative 1, and I is just I. So what this becomes, negative 1 times I is just negative I. And then I to the fourth, okay, I to the fourth is the same thing as I squared times I squared. Remember that you're adding those exponents to get to 4. I squared times I squared. Well, we know that I squared is negative 1 times negative 1, which is going to equal positive 1. So our repeating pattern here, okay, our repeating pattern is I, negative 1, negative I, and 1. You're like, because that doesn't repeat. Well, watch what happens when we do I to the fifth. When we do I to the fifth, that's the same as I to the fourth times I. Well, look at our list. I to the fourth we know equals 1. So 1 times I equals I, which is right back where I started. Look at I to the sixth, okay? I to the sixth is I to the fourth times I squared. Well, I to the fourth is 1. I squared is negative 1. 1 times negative 1 is negative 1. We're repeating that process. I'll give you a guess. What do you think I to the seventh is going to be? If you guess negative I, you're right. What about I to the eighth? It's going to be 1. We can keep going on this pattern, so the pattern repeats. I to the ninth is I to the 10th is negative 1. I to the 11th is negative I to the 12th is positive 1. We could keep going forever and ever and ever. This is a repeating pattern that you need to memorize. The repeating pattern again is I, negative 1, negative I, positive 1. And that pattern continues over and over and over again. So here's how you're going to use that repeating pattern. You'll see a question like example 5 that asks you to simplify I to the 58th power. Now you have a choice. You could literally write that repeating pattern of 4 58 times and see whatever the 58th term of that sequence is, and that would tell you I to the 58th, okay? I do it a little bit differently, okay? So let me show you kind of the shortcut that I use. I take 58 and decide how many times does 4 go into 58 evenly. That means think back to like 4th or 5th grade when you did division and you were allowed to leave a remainder in your answer, okay? So 4 goes into 58. Let's see. Is that 14 times? You know what? Let's actually do the division. So 4 goes into 5 one time, times 4. 4 goes into 16 4 times, so it's 14. Okay, so 14, and then we've got remainder 2. We'd have 14 remainder 2. Well, what's really, really nice about this is you want to look and see what your remainder is. Whatever your remainder is, that tells you which number in the sequence you're going to have. So again, the sequence, the pattern was I, -1, -I, +1. Since we're at remainder 2, I'm at the second term in the sequence. I'm at the second term in the sequence, so it'd be -1. -1. Be the second term in the sequence. So remainder 1, if you get remainder 1 when you do this division, you're going to be at the first term. Remainder 2, when you do the division by 4, you're at the second term. Remainder 3, you'll be at the third term. And remainder 4, or remainder 0, is what that would look like. Okay? Remainder 0, you're at the fourth term of the sequence. Okay? It's very okay if you're like, what, Cosette? That's very confusing. Okay, let's try a couple more, and I think the light bulb's going to turn on for you. Okay? So example 6 says simplify I to the 29th. Okay? So here's what we're going to do. We're going to take 29, and we're going to divide it by 4. Okay? 4 goes into 29 7 times. 7 times 4 is 28. Do the subtraction. We get remainder 1. So remainder 1, I look at the first term of my sequence, my repeating sequence, and I get just I. I to the 29th simplifies to just I. Let's do the same thing with I to the 32nd, okay? So 32 divided by 4 is actually a whole number. It's 8. Remainder 0. There's no remainder left over. So if it's remainder 0, we've got the fourth term in our sequence, which is just +1. Any of these questions, I to any power, is literally going to be one of 4 answer choices. If you are confused or you have any doubts, you can always just you could honestly just randomly pick one of those 4 in the repeating pattern, and you'd have a 25% chance of getting it right, okay? But remember, the way we did that is we divided by 4, find the remainder, and then whatever the remainder is, that tells you which number in the sequence is going to be your answer choice. Okay. Now, example 8 is the same kind of deal. It's just kind of formatted a little bit differently. We have 5i squared times 4. I don't know why that multiplication dot is so obnoxiously huge, but we're going to roll with it. Okay, so when we multiply these, multiply real number part times real number part. So 5 times 4 gives me 20. And then imaginary part times imaginary part. I squared times I is I to the third. Well, think back to your repeating pattern. What does I to the third equal? Okay, I to the third is the third term in the sequence. So it's 20 times -I. And if we clean that up a little bit, we end up getting -20I as our final answer. Just different ways that you can manipulate these powers of I. Again, I can't emphasize this enough. This is so important, okay? It really just comes down to a repeating pattern of 4. Okay, it's a really, really important thing to remember, that repeating pattern of 4. Okay, now the next phase in this is we're going to talk about complex numbers, okay? Operations with complex numbers, and this is what a complex number looks like. The reason that these are called complex numbers is complex numbers have a real part, and they also have an imaginary part. The real part, obviously, is just going to be like a real number like you're familiar with, and the imaginary part is going to be a real number times the imaginary unit, okay, just like we've been dealing with so far. I think you're going to be really pleasantly surprised with addition of complex numbers. So if you look at example 9 here, addition is so easy. What you're going to do here is you're going to add real part plus real part. So, and then you're going to add imaginary part and imaginary part. So when I do this, 3 plus 2 is 5. That's my real part. Plus 5i plus -4i gives me plus 1i. So the solution here, when I add this together, is just 5 plus I. Again, it's just like combining like terms. Combine the real parts, combine the imaginary parts. Okay, same concept on example 10. Real parts, combine those, and non-real parts, imaginary parts, combine those. So 4 minus 3 is 1. And then be careful here. You've got negative 6i, okay? You've got negative 6i minus negative 7i. When you be careful here, when you subtract a negative, okay? When you subtract a negative, that turns into plus, okay? It turns into plus 7i. So negative 6 plus 7i gives me plus I, 1 plus I, final answer. All you're doing when you add and subtract is combining like terms. Okay, the next skill that you're going to see here is how do we multiply, okay, complex numbers. Well, you're just going to FOIL just like you normally would, okay? So first times first, 1 times 3 is 3. Outside, 1 times negative 6i is negative 6i. I stands for the inside. 4i times 3 gives me 12i. And then L stands for the last terms. We have minus 4 times 6 is 24. I times I is I squared. Okay? So now what we want to do is we want to combine our like terms and clean up any I terms that we have. So that gives me 3 plus 6i minus 24i squared. Well, the very last thing here is we're not going to leave this term here as negative 24i squared because we know that we can replace I squared with negative 1. Think back to our repeating pattern. Our repeating pattern, anytime you see I squared, you can replace that with a negative 1. So that really becomes minus 24 times negative 1. Well, negative 24 times negative 1 turns into positive 24. So if we add that with the 3 that we already have, we end up getting 27 plus 6i. Final answer. So not super complicated. I think it's pretty straightforward. You're just foiling like normal. Okay. Example 12 is literally the same kind of deal as 11. I would pause the video now and try that and see what you get. Okay, welcome back. Hopefully you paused it and actually tried example 12. If you didn't, this is kind of awkward, okay, because you should have paused it and tried it. You can even still do it now. I won't know. Actually, I never know if you do it or not. It's the honor system, okay? So I'm going to go through this really, really quickly. Please, 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 if you did not do it, please try to do it. If you did do it, check your answer. So when we FOIL this out, we get 3. That would be minus 9 plus 2 would give me minus 7i. And then negative 3 times positive 2 would be negative 6i squared. I can replace the I squared with negative 1. So that turns into plus 6. So 3 plus 6 is 9 minus 7i. 9 minus 7i is what I got. Hopefully that's right. Did you get that too? All right, let's move on. Okay, we are almost done. These are the last 4 problems, and they go pretty quickly, okay? Example 13. Well, here's what happens when you have an I, or a complex number, in the denominator of a fraction. You are not allowed to leave I in the denominator of a fraction, just like you're not allowed to leave square roots in your denominator. We're not going to leave i's in our denominator either. So to get rid of those, we are going to multiply this by 2i over 2i. Again, this is called a chunky 1. We're just multiplying by a chunky 1 because 2i divided by 2i is still equal to 1. Okay, so multiply the top times the top. So if I do the distributive property, that's going to be 10i plus 2i squared all over 2 times 2 is 4. I times I is I squared. Then you can replace your I squareds with negative 1s. So on the top we have 10i plus 2 times negative 1. And on the bottom we have 4 times negative 1. So if we clean those up, we get 10i minus 2 all over negative 4. Now if you really wanted to get fancy, which I know some of you do, especially those top gunners, okay, I know you want to get fancy. Notice how each one of these numbers is divisible by 2. Okay, each one of those is divisible by 2. Well, what we can actually do is we can go ahead and factor out a 2, And we can rewrite that as 5I minus 1 all over negative 2. That is big baller status right there. If you get all the way to that, that is really, really impressive. Your teacher's going to really like that. Okay? All right, so that was a pretty simple problem because notice here this denominator was just an imaginary part. Okay, it was just imaginary. Now, if you look at example 14, we have a real number as well. So this is called a complex number. Okay? Again, complex numbers are combinations of a real part and an imaginary part. The only change here is that instead of multiplying by just 4i over 4i, we're going to multiply by something called the conjugate. We're going to multiply by something called the conjugate. The conjugate is whatever that denominator is, but just the opposite sign. Okay, so I'll write that word down for you, called the conjugate. Again, so when you have a complex number in your denominator, you're going to multiply by the conjugate on the top and the bottom. Okay, now if you do that correctly, you've got to FOIL the top. Okay, so that becomes 2 plus 3i plus 8i plus 12i squared all over 1 minus 4i plus 4i minus 16i squared. Okay, well, if you look at the bottom here, minus 4 plus 4, minus 4i plus 4i, those cancel out, okay, which is nice. So then if we combine our like terms on the top, I end up getting 2 plus 11i plus 12 times negative 1, because I'm going to replace that I squared with negative 1, all over 1 minus 16 times negative 1. Okay, so clean that up one step further. 12 times negative 1 on the top becomes negative 12 plus 2. I get negative 10 plus 11i all over 1 minus negative 16 turns into 1 plus 16. So I get 17 as my denominator. Final answer. Again, look at your denominator. If you have a complex number, meaning a real part and an imaginary part, a real part and an imaginary part, you multiply by what's called the conjugate, which is just the denominator. Only difference is we change the sign. And then you just simplify it like we've been practicing. Okay, finally, last two questions. These ones should be pretty easy for us, but we change our directions a little bit. Now we're asked to solve for x. Okay, so what I look at here is this is not a trinomial. I don't have a linear term here. I just have an x squared. So what I can do is I can take steps to get that x squared by itself. So first step would be to subtract 32 on both sides. Next step is to divide both sides by positive 2, and we get x squared equals negative 16. Okay. Now, there actually, when we solve quadratics, when we solve second numbers to the second power, what we do is we take the square root of both sides. But remember, when you take the square root of both sides, there are two possible roots or two possible answers that make that true. Okay, there's two possible answers that make that true. You can either have the positive or the negative. So what we do is we put a plus or minus sign in front of that radical. Every time you take the square root of both sides of an equation, you need to have a plus or minus in front of your radical. So we actually saw this problem earlier. Remember, this is that stupid joke that I laughed about probably more than I should have. I'm a little embarrassed. But the square root of negative 16 is that poor little guy who came home from school because all his friends were calling him 4i. Okay, so don't forget your plus or minus. So it's plus or minus 4i. Okay, so these here are your solutions. They are not real solutions. They are imaginary solutions. Okay, so if we looked at this graph, the graph of this function, if I asked you to graph it, would be one of those graphs that never intersects the x-axis, okay? It's going to be a parabola that opens away from the x-axis. It never intersects, okay? Why don't you try number 16, see if you can get your two solutions. Okay, hopefully you actually tried that. I'm going to go pretty quickly through this one and show you what you should have had. So we have negative 3x squared equals 144 as I added 24 on both sides. And then I divide both sides by negative 3, and I get x squared equals negative 48. I think that's true. Yeah, is that true? Yeah, I think that's true. Okay, so negative 48. So then I take the square root of both sides. And remember, when you take the square root of both sides, you need a plus or minus in front of your radical. Check your work. Did you do that? A lot of people forget that. I'm telling you, a lot of people are going to miss points because they forget their plus or minus sign. So now all I have to do is I have to simplify the square root of negative 48. So that becomes plus or minus the square root of negative 1 times 16 times 3. 48 I can split up to 16 times 3. Okay, so then what I have is I have x equals plus or minus. 16 comes out as a 4. Negative 1 comes out as an I. And that poor 3 is trapped in the radical forever. Okay, it's the square root of 3. So your solution here is x equals plus or minus 4i root 3. That's how you say that. Plus or minus 4i root 3. Okay? Well, guys, that's it. That's all I got for you. That's complex numbers. I know it was a lot of material, and I know it went pretty quick, but I trust you guys to be able to handle that. Talk to one of your teachers. If you're having trouble with it, go back and watch this video again. If you thought that those comics were funny, go ahead and like this video and leave me a comment in the comment sections. I love to hear from you guys. I say that, but nobody ever comments. So you guys are awesome. Hope you enjoy the rest of your night, and I'll see you next time.